Next, I'll provide you with a program that I've written which uses the GMP library to plus it uses OpenMP for the parallel processing. Let me plug in the data card. I'm plugging in a jump drive with my code in there. Okay, so let's look him over. Okay, what I want to look for is over here. I want the composite, and I want the input data, and I want the program itself. Okay, so let's click on that. Well, let's first create a place for it to be at. Where's Pi? Home, Pi, create folder, data. Create folder prime. Okay, so now let's go back. Raspbian primes, composite, input. No, wrong one. Cancel that. Composite and input. There we go. Those are the ones I want. Copy. And I want to put these over on data. Paste. Okay, now I want the program. There it is. Copy. And I want to put that on prime. There it is. Paste. Now I'm going to bring in an SD card from another Raspberry Pi so I can get the compile and link instructions. Okay. Cancel that. Okay, let's see. I want there. Let's see, is it prime? Let's see what's there. Okay, there it is. CC process. There it is. Copy. And I'll put them over here on prime. CC process is just the commands to compile and link the program. There you go. You need to include the -f OpenMP to tell the processor to do that you're going to have a parallel program, an OpenMP program, and you need to include the library GMP. There we go, right there. And that's the only difference. So let's go to our there. Let's see. CD prime. Oh. CD prime. There we go. Okay, you need to change the mode on the CC so it'll be executable. ./cc. Okay. Warnings, but no errors. So that's good. Now what we need is the command to execute the program. So we do that over on h.t. Let's see. Okay, what are you? I keep a history of everything I run in a file so I can just send it from one machine to the next. Okay, here we go. I think it's this one here. Okay, let me copy him. Go back to my... Okay, so let's just CD on that to get to the right library. Paste. Okay, now I need to do a few changes. Okay, and the name of the input data isn't pre-processed, it's something else. Okay, what's the name of it? It's a data input. That's what it's called. Okay, so let's run him. Oh yeah, you need to if you're going to run this program, you always need to check heating because your boards are liable to overheat. So what I do with my little bitty Raspberry Pi is I have a fan I bought and I turn that on. So that's what I'm going to do right now. Let me see. There we go. Otherwise, he's liable to overheat. Render. There we go. Okay, so we got some on the 10th iteration, so we're doing good. We got some on the 263rd iteration. You can just touch the card with your fingertips and see that, yes, it's overheating a little bit. Okay, now I'm going to stop it here because that's as far as I really want for it to go. It'll take it this Raspberry Pi only has 4 threads on there, so it would take it a while to reach the billionth prime, but it will reach it. So I'm gonna stop right there. What I really wanted to see is that it would run and it would give me a verify. Okay, now we're going to look at the program that was running. process. And we're going to look at its output. We're interested in the verify2 that I saved earlier. And we're going to bring up Mathematica. The main reason for loading the Raspbian system is that you get a copy of Mathematica. And it's for free. Okay, there we go. Now let's look at the program here. Okay. There's the GMP library right here, or the header for the GMP. And here is the header that you need for the parallel, for the open parallel system. Let's see. Here's the output for the here's the file name for the verify, which we will be including in argument 7. EMPZT is used to identify the large integers. And if you identify them, you create them, and then you have to initialize them. All I'm interested here in this part of the code is how many lines are there in the input data, because I want to know what size my array has to be. Here I'm just inputting I'm loading in the number that's going to be factored. This factoring is only for small numbers. Here I'm creating the array, or getting memory for the array. I'm now loading the arrays with the data that's in the file. I've opened the verify file. Now, the first time I run this, the first time I process the data in the arrays, I'm going to be creating my verify file. So I output the number that is in the last element of the array. And that's how you output a large integer. Then I output a carriage return, or line feed. Okay, and then I need to process the elements of the array. I do that in parallel. The Raspberry Pi has 4 processor, 4 cores, so it has 4 threads. Each thread does one element of the array. I first make a copy of the array. I copy what's in array 1 over to array 2, and I copy it such that it shifts the value one cell. It just shifts it over, and then I do an add, and that's all. This process in here is everything that has to be run in order to go from one composite number to another composite number. These composite numbers are made up of the sequential primes. So you start out with like, what is it? It's 2310. So I think it's 13. You start out with 13, 17, 19, and the primes will be sequential in the composites. And then you go from one composite number to the next composite number. And then you go to the next one and the next one. After I finish processing the verify file, I then go into the main loop. So I do the same thing that I was doing before. I first shift the elements of the array and copy them over to array 2, and then I add array 2 to array 1. I then multiply array 1, the last element of array 1, I multiply to hold, and then I do a mod so that only the modulus portion is contained in hold. And then I do greatest common divisor between hold and the number being factored, and I put that in B, M underscore B. And then I check to see if he's greater than 0. If he is, then I output the at which iteration that was true. If the mod input data is designed to decrease the size of the numbers inside the array. The first you can either run it without doing this, in which case you can see what primes you're at, or you can set this greater than 1, and then what happens is that you're running with smaller and smaller numbers, so your speed goes up. When all of the iterations are finished, then I'm through, and so I write out my array at this point in time. So you could restart at this point in time if you wanted to. I then clear my arrays, free them, and that's it. Now let's look at the data. Here is what the verify looks like at the first iteration. So what we do is we go over to Mathematica, and we say print print factor integer, put in the value, and then we evaluate it. And so we see we start at 13, 17, 19, 23, 29, 31, 37, 41, 43. These are in prime number and then the exponent. And we see that the first iteration, what that large number right there is a composite of all of the first sequential primes. And he goes all the way to 2311. So the algorithm jumps from this number over to the second number, and then we look at the second number. So let's highlight you. And we evaluate the array, the cells. And we see that we're going to have some of the smaller primes show up still, because the sieve will generate composites as well as primes. But once we get past these few, we see we start at 2333, and then 2339, and then 2341, and so forth. Now let's evaluate the 10th element in there, the last element in this verify array. And we evaluate. So we've got some small numbers there, and then it starts again at 20, 80, 07, and then 20, 80, 80, 09. So the algorithm jumps from one highly composite number with sequential primes to the next one, to the next one, to the next one. And it'll do this for however many iterations I run it. And then all I have to do is find the greatest common, compare the number I'm looking for against the numbers that are being generated, all of the prime numbers that are being generated. Each iteration has the capacity to generate maybe 480 primes at one time. And if I'm working on the modulus, then the algorithm goes fairly fast. Of course, not with the, it depends on how many threads I'm running at one time, which for the Raspberry Pi, you can only run 4 threads. It takes something like 30 minutes or so to reach the billionth prime. And that's it.